Now, covalent bonds are completely different, okay? Covalent bonds happen when you have sharing of electrons between atoms, okay? And this is section 7.2. Now, we know that atoms are shared with one another because hydrogen, for example, is a diatomic molecule. Now, hydrogen is a nonmetal, okay? And covalent bonds happen in nonmetals, all right? So whenever you have a nonmetal, like say, for example, hydrogen, bonded to another nonmetal, say, for example, chlorine, you're going to have a covalent bond between these two. There's going to be electrons that are shared between those two different atoms. An ionic bond, as you remember, is an ionic compound, which is a metal-nonmetal combination, okay? Now, this bond that's shared between two different atoms can be perfectly covalent if the atoms are identical, okay? So if you have identical atoms, that share electrons, okay, we say that it is 100% covalent. Or another way of saying this is that it's nonpolar, okay? 100% nonpolar. So an example of that would be two hydrogen atoms, for example. Two hydrogen atoms come together to form H2, or chlorine. Two chlorine atoms come together to form Cl2. Okay, so there's a chlorine-chlorine bond there, and each of these chlorine atoms is perfectly sharing the electron with the other, okay, in perfect harmony. Now, in the case of hydrogen chloride, for example, if you have dissimilar atoms, they can also share electrons, okay? But it's called a polar bond. So this is the key word here. Nonpolar up above, and this is called polar, okay? It's still a covalent bond because electrons are shared, okay? Whenever you have sharing of electrons, it's called covalent, but they're unequally shared, so it's a polar covalent bond, okay? So what does that look like? Well, it would be, for example, a hydrogen coming together with a chlorine, and that forms HCl, right? Hydrogen chloride is a gas. And now what you want to do is look at the electronegativity values of these two atoms. Well, let's first draw a little picture of this. Hydrogen is smaller, okay? And chlorine is a lot larger, okay? So it's kind of an unequal kind of drawing like that, okay? And now chlorine is kind of a hog. It likes electrons more, and so we draw what's called a bond dipole, okay? This arrow right here is called a bond dipole. And it shows the unequal distribution of electrons in a, it shows the electric field basically. So the side of the arrow that kind of looks like a plus is going to be the plus side of the molecule. All right? If chlorine is stealing the electrons a little bit, the hydrogen is going to be a little bit plus or deficient, and the arrow points to the negative side of the molecule, okay? So the arrow is going to be the negative side of the molecule. Now we can also represent this with Greek letters. We can draw out the bond right there. We'll talk more about the nature of that line and what that line really means. But we can write delta plus and delta minus. Now delta means partial, okay? It indicates the polarity of the HCl bond, okay? And delta minus means, partial negative, okay? So there's two different ways to indicate how the electrons are unequally distributed in the HCl molecule. We can use a bond dipole arrow to indicate how the bond is formed between two atoms that don't equally share electrons, or we can write delta plus and delta minus above the respective atoms in this unequal partnership, okay? Now, whether a bond is nonpolar or polar covalent is determined by a property of the bonding atoms called electronegativity. What you want to see here is that on this corner, increasing this way, we have high electronegativity. And this way, either down a column or to the left, we have decreasing electronegativity. Okay? And this is derived from Pauling. Linus Pauling was the one who advocated eating, vitamin C to cure the common cold. Gosh, I wish it would cure COVID. And then the higher electronegativity are upper right of the periodic table. So what does that mean? It means that if you have, and here's hydrogen, okay? So let me switch to green, I guess. Here's hydrogen, and here's chlorine, okay? So hydrogen has an electronegativity of 2.1. Think of that as the strength of pull on a bond, okay? And this is a line, think of that as a rope. That chlorine is playing tug of war, okay? And chlorine has a strength of 3, okay? Electronegativity value of 3, okay? So who's gonna win? Chlorine's gonna win. How do we draw the winner? We can draw that with a delta minus. So remember, the war is for the electrons. So the chlorine's pulling the electrons, and it's winning a little bit compared to the hydrogen, okay? Let's look at another bond. Let's do another one. Let's do oxygen and carbon. You have this molecule here. I don't want to overwhelm you too much, but these molecules can be quite interesting and very long and big and large and all that. But I want to focus in on this bond right here, okay? This molecule right here is the structure of methanol. Okay, methanol. And so let's take a look at carbon. Where's carbon? Oh, here's carbon. Carbon has a value of 2.5. Okay. Oxygen is over here. It has a value of 3.5. Okay, so who's the winner? Oxygen is the winner. I'm going to not use delta plus and delta minus. I'm going to use the dipole arrow to indicate who the winner is. Okay, we always point to the winner. Okay, the dipole arrow points to the winner. So oxygen is more electronegative, so the polarity is going to be that way. Okay, we are of course going to be focusing only on molecular compounds, which are made of nonmetals and maybe metalloids at the most. So we're going to talk about these atoms right here and hydrogen. Okay, so Linus Pauling did a lot of research and everything. There's a little picture of him in the book if you want to take a look at that. Okay, so let's do a little bit of math here. Here's your guide for understanding if things are going to be polar or nonpolar or something like this, okay? So, if the difference in electronegativity I'm going to use this notation later, so I'll define it here. Okay, so if the difference in electronegativity is 0, okay, we are going to call that pure covalent. Okay, and we commonly call this nonpolar. Okay? If your, and I say 0, but you know, it's less than 0.4, okay? 0 to 0.4. All right, so if it's really small, we call it nonpolar. All right, nonpolar. An example of that would be methane. Okay, so 0 to 0.4, keep that in mind. Let's look at methane. Let me see if I can draw in a color that you'll see, maybe just black here. So we have methane. Methane is CH4, as you remember from previous chapters. Carbon is 2.5, okay, 2.5. Hydrogen is 2.1, okay. 2.5 minus 2.1 is 0.4. So we would say the CH bond is nonpolar in methane. Nonpolar, okay? So that's an example of a nonpolar bond, okay? Let's see if we can squeeze that in here. Example. CH, all right? Now, what if we got something between 0.4 and 1.8? So somewhere in between here. We call this intermediate, okay, intermediate. We call this a polar covalent bond, okay? Okay. I never really call it pure covalent, I just call it nonpolar. All right, so what's an example of that? Between 0.4 and 1.8, an example of that would be methanol. So here, oxygen is 3.5, carbon is 2.5, so that difference is 1.0, okay? The difference between the carbon and the oxygen. So if I look at that, oh, that falls in between, doesn't it? So an example of that would be oxygen bonded to carbon. So the CO bond or the OC bond is polar covalent. It's a polar bond, all right? Now, if you have something that's more than 1.8, difference in electronegativity, we call this ionic, okay? The book would call it ionic too. An example of that would be sodium chloride, right? Sodium and chlorine do not share electrons. Sodium is a metal, and chlorine is a nonmetal. They're just two opposite, okay? So let's draw that, sodium and chlorine. Who would be the delta plus? Well, sodium is +1, right? Because that's the ionic charge, and chlorine is -1, so that's the ionic charge. Chlorine is 3.0, sodium is 0.9. So, you know, you can do the math here, and that's huge. That's 2.1 as a difference in electronegativity, okay? So the delta En there is, what did I say? 2.1, and that's definitely greater than 1.8. So we would call NaCl ionic, okay? I'm not going to draw a line between those two atoms because there is no line. It's just an ionic bond, okay? So you've got a whole table, an example 7.3. They ask you to calculate the CH, CN, CO, NH, OH, SH. And what do you need to be able to do? You need to be able to label delta plus, delta minus on atoms, okay? So if you have an OH bond, you need to be able to describe it as being, okay, delta minus and delta plus. And you need to look at the periodic table to see that and know that and to write that down, okay? I don't care if you're able to calculate the change in electronegativity. Then what you need to be able to do is to label it as polar, all right, polar. And these are both nonmetals, so that's how you know it's a polar covalent bond. Okay, if I gave you a metal and a nonmetal, you would of course know how to label it, all right? All right, so that's where I want to kind of end this here, and I'll pick up with the next video talking about Lewis structures, which is a much more interesting way of describing bonding in molecular compounds.